In Jesus' name. Father, we thank you for a moment like this. We bless and appreciate you because you are faithful. We thank you for mighty works you're stretching out upon our lives. As you are about to study, Lord, grant us the grace to recall, memorize, apply everything that we explained in Jesus' mighty name. Amen. So, in today's class, we'll be studying equilibrium of forces. Equilibrium of forces. And you know, in SS1, we studied about equilibrium of forces. And for the course of our exam, the WAEC or NECO syllabus, equilibrium of forces always surface in our exams. Now, if you look at, I'm going down my slide. If you look at the assignment there, we have 1997, 2007, 2011, 2014, 2016, 2017. Almost every year, you have equilibrium of, I just selected some here. So in the course of performing or solving these questions, you'll be able to see more of these equilibrium of forces. So we're going to study them from the beginning, based on what we did in SS1. And under the equilibrium of forces, you are expected to do some assignments. And these assignments should be sent to the contact on the screen. Look at this contact on the screen. Derek, can you see my contact on the screen? Derek, can you see my contact on the screen? Derek, can you hear me? Derek, Olorunsiyi, can you hear me? Isaac, can you hear me?
Yes, sir.
Yes, sir.
Okay. So I said you are expected to do some assignments. Now, as I said earlier, now this lockdown is an opportunity to cover our scheme, go through our scheme over and over to perfect everything. Remember, our practical is very important. So whatever you are doing, you should be able to plot graphs, find intercept and slope, state precautions, which we'll be doing in our next class. In our next class, we are going to be carrying out some practicals. So now in this class, I expect you to come along with your calculator, your writing materials. Now, equilibrium. Olorunsiyi, define equilibrium for me. What do you understand by the term equilibrium of forces? Can you explain equilibrium of forces for me? Olorunsiyi. Derek, what about you? Can you define the equilibrium of forces for me? When is a body said to be at equilibrium? When is a body said to be at equilibrium? Okay?
I think it's when all this is act.
What? I'm all ears. What do you understand by the word equilibrium? When is a body said to be at equilibrium?
So when the body acts at the same force, when all bodies act at the same force.
Okay. Okay. A body is said to be at equilibrium if it does not rotate or move. If a body does not what? Rotate or move, then it's said to be at equilibrium. That is, if the sum of forward forces are equal to a sum of backward forces, then that body is said to be at equilibrium or at rest. Now look at this. Can you see my board? Can you see my board? Daddy, can you see my board?
Yes, sir.
Okay, Esther Peters, please.
Yes, sir.
On your video. Okay, now if you look at the board, I have a box. Let's assume this is a log of wood. Now, if this log of wood is placed on a horizontal surface, look at this log of wood, it's placed on a horizontal surface and it is not moving. There are four forces acting on it. Number one, we have the normal reaction. R. 2, we have the weight. Then to my right hand side, I have the pulling force, FP. Then to this side, I have my frictional force, FR. These are the 4 forces that act on this block of wood. Block of wood. Block of wood. Now, these are the 4 forces that act on the block of wood. Now, this block of wood is at equilibrium because the forward force, this upward force, is equal to the downward force. And this pulling force is equal to what? The frictional force. Then the body is said to be at equilibrium. Now, the body is said to be at equilibrium if it does not rotate or move, if it is stationary, or if it is at rest. When a body is at rest, it has weight. A body at rest has weight. So now, our next slide. Now look at this. Equilibrium. Our subtopic is moment. So at the end of this class, we should be able to define the moment of a force, the principle of moment, the equilibrium of forces, types of equilibrium, and application of couple, which we did in SS1. So now let's move on. Now, a body is said to be in equilibrium if, 1, it does not accelerate or rotate. That is, if it is at rest. When a body is at rest, then it's said to be at equilibrium. If the body does not move or accelerate or rotate, then the body is said to be at equilibrium. Then number 2, a body is said to be at equilibrium if it moves in a straight line with a constant velocity of rotation at a constant angular velocity of rotation at a constant angular velocity when acted upon by several forces. Now look at this. If you look at this body here, this body is acted by several forces. I have the pulling force, the frictional force, the normal reaction, and the what? The weight of the body. Then the body is said to be at equilibrium. Now, under equilibrium, we'll be considering the moment of a force. What do you understand by the word the moment of a force? Moment is different from momentum. Moment is different from what? Momentum. In our last class, we talked about momentum. I said momentum is okay. Now, moment. I said there's difference between moment and momentum. They are not the same. This is momentum. Momentum and moment. They are 2 different words, but they are all vector quantities. Both momentum and moment are what? Vector quantities, but they are different. Momentum is talking about the product of mass and velocity, while moment is talking about the turning effect of a force. It's talking about what? The turning effect of a force about a point. It's talking about what? The turning effect of a force about a point, or the product of force and the perpendicular distance from the point to the line of action of the force. That is, if I have something like this, this is my distance, 3 meters, and this is my weight. This is my weight or force. If my weight or force is 5 newtons, if I want to calculate my moment will be 5 times 3, which will be equal to 15 Newton meter. Which will be equal to what? 15 Newton meter. Can you see that now? This is moment. So moment is the product of force and perpendicular distance to the line of action of the force. Moment is different from momentum. Now, moment and momentum, they are all vector quantities. They are all vector quantities because they have magnitude and direction. They are all, now look at it. That is, moment is equal to force multiplied with perpendicular distance of pivot to the line of action of the force. The line of action of the force. Now, what we are talking about here is that if I have a rule, you did this experiment in SS1. I taught you this experiment in SS1. Now, if you have a rule, and this meter rule has graduation from 0 to 100. So if a mass of 50 grams is attached at 10, look at it, this is 10. And another mass is attached at this level of 100 grams. And this is the center of pivot. The center of a meter rule is what? Michelia, what is the center of a meter? What is the center of gravity of a meter rule? Is Michelia there? Michelia, Fee, please on your videos. On your videos. Oh yeah. Buzu, what is the center of gravity of a 100 centimeter rule? What's the center? Buzu, are you with me?
Yes, sir.
Okay, what is the center of gravity?
50.
50. That's the center. So now if they're asking you to calculate the moment, because we are talking about moment of a force, we said the moment of a force is the product of force and perpendicular distance of pivot to the line of action of the force. So now, in this diagram, what I've drawn here, can you see the board? Tayo, can you see my board? Tayo, can you see my board? Tayo, can you see my board?
Yes, sir.
Okay. Now, if you look at this moment is divided into two parts. We have the anti-clockwise moment. Anti-clockwise against the clock. While this side is the clockwise. So if I ask you, or you are asked to calculate the anti-clockwise moment about the pivot is the point of fulcrum. Where the fulcrum is, look at the fulcrum. This triangle is the fulcrum. So if you are asked to calculate the anti-clockwise moment of the force, anti-clockwise moment of the force, if you want to calculate the anti-clockwise one, which is ACWM, will be equal to force multiplied with perpendicular distance. Multiplied with perpendicular distance. Look at that. Force multiplied with what? Perpendicular distance. And if you want to calculate the force multiplied with the perpendicular distance, you need to calculate this. Force is measured in newtons, but they gave us the force here as 50 grams. So you need to convert these 50 grams to kilogram before further conversion to newtons. So we have 50 grams. How do you convert these 50 grams to kilogram? What do you do? Fee, on your video. Fee, how do you do that? How do you convert these 50 grams to kilogram? Fee, I'm listening. Fee, are you there? Okay, Aliu. Aliu.
So,
Aliu, on your video. Oh, Emmanuel. Okay. You don't want to say anything. Okay. No problem. Now, what I'm trying to say here is that I'm saying that Aliu, you are there. Aliu, I want to convert this 50 grams to kilogram. What am I expected to do? Because they gave us our weight, our force to be 50 grams. And I told you earlier, even in SS1, I said you don't use sub SI unit for calculation. Use the SI unit. So you need to convert these 50 grams to kilograms. So what are we expected to do? Oyaliu.
I divide by 1,000.
Say anything. Aliu. Tayo, what do we do? Tayo.
So I divide by 1,000.
Okay, thank you. So you divide this 50 by 1,000. So I'm going to have 50 divided by 1,000. It will now give us in kilogram, isn't it? So everything will now be in kilogram. Multiplied with, we need to convert it to Newton. So if you want to convert to Newton, you multiply with what? 10 meters per second per second. So you multiply it with 10. You know, this 10 was not given, but you should know that force or weight is mass multiplied with what? Acceleration. If it is weight, it's mass multiplied with acceleration due to gravity. Then if it is force, it's mass multiplied with acceleration. So you do that. Then multiply with perpendicular distance. What will be our perpendicular distance now? From 10 to 50. Who will help us now? Remember, we said moment is force times perpendicular distance. HM.
Sure.
Now, what is my perpendicular distance at the anti-clockwise moment side? Can you see my board? The pivot is 50.
Yes.
The mass is at 10. So what will be my perpendicular distance? Say something. Just say something. Say something. Isaac, help us.
Sir, please come again.
I said, you know, moment is force multiplied with perpendicular distance. And my force, they gave us 50. Look at it here. They gave us 50. So if I want to come 50 grams, so if I want to convert to Newton, you know, definitely I have to convert these 50 grams to kilogram, then multiply it with 10. Isn't it? Then now, how do I get my perpendicular distance? If the pivot is at 50 and the weight is suspended at 10, what do I do? Someone should help me now. Buzu, say something. Buzu. Okay, now can you see 50 here? Buzu, can you see 50?
Yes, sir.
Okay, and what is this?
10.
10. So the distance will be 50 minus 10. 50 minus 10 is what?
40.
40. So my distance now will be 40. Now this 40 now has no scale. So use it like that. If the 40 is in centimeters, you know, definitely it's 100 centimeters. So you need to divide this 40 by 100. Because you know that if you are converting from centimeters to meter, you need to divide by 100. Can you see that now? So now you can solve from there. So when you solve, this 0 will go without 0. This 0 will go without 0. 5 divided by 10 is 0.5. Multiply with 0, we go with 0. Then 4 divided by 10 is 0.4. Then you multiply 0.4 with 0.5. Then the answer will be Newton meter. The answer will be what? Newton meter. That is how we calculate the moment of a force. Now, that is the moment of the anti-clockwise. Now, for the body to be at equilibrium, the clockwise moment must be equal to the anti-clockwise moment. It's just like in real life. Someone that walks like this does not walk at equilibrium. Someone that walks with one shoulder down is not walking at equilibrium. Is that taking? But you have to walk with a square shoulder. When a man is walking with a square shoulder, he's walking or is moving at equilibrium because the rate of forces on your left-hand side is equal to the rate of forces on your right-hand side. Then that body is said to be at equilibrium. Next, we have, we said the moment of a force is measured in Newton meter. That is a derived unit because force is measured in newtons and distance is measured in meter. So the unit will be Newton meter. Now, for objective tests, which other quantities have the same unit as moment? Or yeah, give me 4 quantities. I taught you in SS1. Give me 4 quantities that have the same unit as moment.
Impulse.
Give me 4 quantities that have the same unit as moment. Remember, recall from SS1 work. I'm all ears. Michelia, Oya, give me 4 quantities that have the same unit as moment. You know, 4 quantities that have the same unit as moment. Okay, Achem, 4 quantities that have the same unit as moment. Achem. Achem. Oya, Derek, 4 quantities that have the same unit as moment. Derek, 4 quantities that have the same unit as moment.
Sir, couple.
Couple, yes.
Couple.
Yes. Number 2. I'm listening. Oya, Tayo. 4 quantities that have the same unit as moment. They have the same unit. They have the same dimension. Oya. I'm listening.
I said impulse.
No. Try, but you tried for answering me. Try again. Oya, Tayo. Impulse and momentum, they have the same unit. Impulse and momentum, they have the same unit as Newton seconds or kilogram meters per second. But moment, now listen, I will write them down so that you will not forget. I'm going to write them down. Now, if you look at this, because of objective text, let me ask you which of the following quantities have the same unit as moment. Now look at them. We have torque. We have couple. We have work. We have energy. All these quantities have their unit as Newton meter. Their derived unit is Newton meter. Look, I repeat, torque. Torque. T-O-R-Q-U-E. Couple. Work. And energy, they have the same unit and the same dimensions as moment. They have the same unit, they have the same dimension. Now, how is the dimension of any of them? Let's pick work. Work is force multiplied with displacement, which is represented by S, F multiplied with S, like this. Now, F is ma, mass times acceleration. Displacement is still displacement. Now, m, the dimension for m is capital letter M. The dimension for acceleration is lt raised to the power of -2, multiplied with the dimension for displacement is length, capital letter L. L times L is squared L. So I have capital letter M, capital letter L squared, capital letter T raised to the power of -2 in squared bracket. This is the dimension for all these quantities. This is the dimension for work, the dimension for energy, the dimension for couple, the dimension for torque, the dimension for moment. They have the same dimension and they have the same units. Any question so far? Achem, any question? Isaac, any question? Isaac. Achem, Aliu, any question?
No, sir.
Okay, now let's proceed. In the absence of any question, we'll proceed. Now we'll go to the principle of moment. What is the principle of moment? What does the moment of a force depend upon? Now, the principle of moment states that if a body is in equilibrium, then the sum of the clockwise turning moment acting upon it about any point is equal to the sum of the anti-clockwise turning moment about the same point. What he's saying here is, this diagram I drew earlier, this is what he's talking about. The principle of moment states that the sum of the clockwise moment is equal to the sum of the anti-clockwise moment. Now look at it. Now, if this is a uniform meter rule, a uniform meter rule has its graduation from 0 centimeters to 100 centimeters. Then the center of gravity is the point where the resultant force acts. So at this resultant point, or the center of gravity will be at the 50 centimeter mark. Then at the 50 centimeter mark, let's assume that one force, let's say force 1, acts on my left hand side, and another force F2 acts on my right hand side. Now, depending on the principle of moment, the principle of moment says that the sum of the anti-clockwise moment is equal to the sum of the clockwise moment. CWM means clockwise moment. Then ACWM means anti-clockwise moment. What the principle of moment is talking about here is, let's assume at this point is 2 centimeters. What will be the distance from 50 to 2? Oh yeah. Let me ask someone here. Oyafi, what will be the distance from the pivot to 2? Oyafi, say something. Fi, are you there? Oya, Aliu, help her.
You good.
Hey, Aliu, what will be the distance from 50 to 2?
I don't know, sir.
Okay, now look at it. This is 2. This side has been cut off. So the distance will be 50 minus 2. 50 minus 2 is what?
48.
48. So my anti-clockwise moment will be F1 times what? 48 centimeters. Can you see that now? Then if the pivot here is at 80, if the body is suspended at 80, if F2 is at 80, what will be the distance from 50 to 80? Oh yeah, Tayo. What will be the distance from 80 to 50? Tayo, say something. Tayo, I'm listening. What will be the distance from 80 to 50? Tayo, not say anything. Tayo. Wow. Oh, Derek, what will be the distance? Derek. What will be the distance from 80 to 50? It's subtraction now, 30. 80 minus 50 is 30 now. So that means my clockwise moment will be equal to F2 times what? 30 centimeters. Now recall that I said these distances should be measured in meters. So this 48 centimeters should be converted to meters by dividing by what? 100. The same thing with our 30. That is what the principle of moment is talking about. He said that sum of the clockwise moment must be equal to the sum of the anti-clockwise moment about the point. That means F1 multiplied with 48 will be equal to F2 multiplied with what? 30. This is what he's saying. That is what the principle of moment is talking about. Now, the principle of moment came out in 2007. It came out in 2007 calculations. Okay? So, and you know, in our Q&A, we use Tonard. So, ensure you have Tonard with you. Tonard. Tonard has about 98% accuracy in terms of past questions. So, we use Tonard. Next, a couple. What is a couple? Isaac, what is a couple? Isaac, what do you understand by the word couple? Okay? Isaac, what is a couple? Isaac, what is a couple?
Married people.
What do you understand by the word a couple? Isaac, say something. What is a couple? Isaac, I'm listening. What is a couple? What do you understand by the word a couple? Say something, just say anything. What you have in mind may be the answer.
I don't know.
No, just say anything. Say something. You said something earlier. What do you understand by a couple?
I don't know.
No, you said something. I heard you say something. Repeat what you said earlier. Then I will correct you. Say it.
I said married people.
Okay, thank you.
Married people.
Now, it's correct. What he's saying is correct. Now, married people attempt to be a couple because they are opposite sex. They are equal and opposite. They are what? Equal and opposite. So a couple is a pair of forces that are equal in size but opposite in direction. But what? Opposite in what? Direction. That is why even in the Bible they said the couple are one. They say 1 + 1 is equal to 1 because they are the same, but they are opposite. They are what? Opposite. One is a male and the other one is a Isaac. One is a male and the other one is a what? Female. You got it now? So a couple is a pair of forces that are equal in magnitude but opposite in direction. One is positive, the other is negative. It's like action and reaction. Action and reaction are equal in size or equal in magnitude, but opposite in direction. Opposite in what? Direction. Like action, reaction. One is positive, the other is negative. They are coming from opposite direction, but the size of my palm are the same size. If one is greater than the other, that means I'm sick. It's either I have boil on my palm. But now, if you look at my palm, they are equal in size. That is equal in magnitude, but they are moving from opposite direction. So this is a couple. This is an example of a couple. Is that taken out? It's like a slap. If I slap the board, two things will take place. I have action. Action will produce the sound. Reaction will produce pains on my palm. So it is action and reaction. They are equal in size, but opposite in direction. Now, our definition. The definition for a couple is a system of two parallel and equal forces acting in opposite direction. It's a system of two parallel and equal forces acting in opposite direction. the resultant force is 0 because they are equal in size. What we mean by the resultant force, its action is equal to plus 2 newtons. Reaction will be minus 2 newtons because they are equal in size but opposite in direction. So now the resultant, if I want to calculate my resultant force will be A plus R, which will be equal to plus 2 minus 2. Everything is what? 0. Can you see that now? So action, the summation of action and reaction is 0. The resultant force is 0, but the resultant moment is not 0. The resultant force is 0, but the resultant moment is not 0. Like this. This is how we represent a couple. This is how we represent a couple. Now, I will draw this circle. This is the center. Okay? Now, this force is F1. The other force is F2. They are equal in size, but opposite in direction. Now, if the distance from this point to that point is 2 meters, can you see that now? And F1 is equal to plus 3 newtons. F2 is equal to minus 3 newtons. Look at the board. Can you see that? These two forces are equal in size, but opposite in direction. It's just like the steering. When you are driving, when you are driving, what you are doing, you are carrying out a copular force. The forces are in equilibrium. One force is moving up, another one is coming down, like this. So they are equal in size and what? They are equal in size, but opposite in direction. But they have the same magnitude. Now, if one happens to be greater than the other, the car will what? Will negotiate a bend. Daddy, can know you can drive. Daddy, can you drive? Can you drive?
Yeah, I cannot drive. You cannot drive.
Sure, sir.
Can you drive, Derek?
Sure, sir.
Now, if you are driving,
Right.
if one is greater than the other, definitely you will negotiate a bend to the right. And if the one from your right is greater, that means you will negotiate a bend to the left. So they must be equal and opposite. Are you following now? So the copular forces must be equal and opposite. Now, we said the resultant force is 0. That means if you add plus 3 to minus 3, the answer will be 0. But the resultant moment is not 0. Why is it not 0? Now look at it. Moment, this is our distance. Moment is force times perpendicular distance. My force is 3 times 2. Everything will be equal to what? 6 Newton meter. You see that it's not 0. That is the resultant moment. The resultant moment is what? Not 0. Can you see that now? Even if I use my 3. Now, if I want to calculate the upward resultant moment, I will not use minus. Minus sign is indicating opposite. So anytime they say calculate the resultant moment upward, don't say minus 3 times 2. You say 3 times 2 because that sign there is telling you that it is what? An opposite force. That is why it carries the negative sign. It's describing the force. Couple produces rotational motion. Couple produces what? Rotational motion. Produces what? Rotational motion. Couple produces rotational motion. That means a couple, when you're driving, the steering has a circular shape. So it produces what? A what? A rotational motion. And rotational motion is the motion of a body about a point or about what? A fixed point. Can you see that now? So that is it. Next, we have application of couple. Where can we use a couple? I think they asked it in one of the years. They said students should state the application of a couple. Where can you use a couple. So Isaac, don't say husband and wife again, no. Don't say husband and wife. A couple is a pair of forces that are equal in size but opposite in direction. Now, applications of couple. Number one, a couple is used in turning on and off a water tap. The water tap, when you turn your water tap, what you are doing, you are carrying out a coupler force. Couple. Okay? Because the couple, the tap has two directions. It has the clockwise direction and the anti-clockwise direction. If you want to switch it on, you move it towards the clockwise direction. If you want to switch it off, you move it towards the what? Anti-clockwise direction. So that is an example. That is where a couple can be applicable. Then the second one is the action of a corkscrew. Do you know a corkscrew? Achem, what is a corkscrew? Achem, what is a corkscrew?
So that thing, when you buy wine.
Thank you very much. Achem, I believe you. I believe you 100%. Okay? Like Pure Heaven. Maybe you want to take Pure Heaven drink. That is the corkscrew. So it operates on the application of a couple. Oh yeah, who can give me another example? Give me another example apart from these two examples of a couple. Where can a couple be applied?
The steering.
The steering of a vehicle. The steering of a vehicle uses the application of a couple. Thank you. Next, we're going to be considering the conditions for equilibrium. The conditions for equilibrium of rigid bodies under the action of parallel coplanar forces. What is a coplanar force? We have two kinds of forces here. We have collinear forces and coplanar forces. What is a coplanar forces? What are coplanar forces, please? What are coplanar forces? Oh yeah, I'm listening. Oh yeah, Noel, what are coplanar forces? What are coplanar forces? Omachonu, what are coplanar forces?
Sir.
I'm listening. What's a coplanar force? Okay. Coplanar forces are forces that are on the same plane. Are forces that act on the same plane. The same force. Forces that are acting along the same plane are coplanar forces. Forces that are acting along the same line are collinear forces. Are what? Collinear, because they may ask you, what are collinear forces? We say collinear forces are forces that act on the same line. They are collinear. What are the forces that act on the same plane? Are coplanar. Now, the conditions, number one, the sum of forces in one direction must be equal to the sum of forces in the opposite direction. Just like the sum of clockwise moment is equal to the sum of the anti-clockwise moment. Then number two, the sum of the clockwise turning moment about a point is equal to the sum of the anti-clockwise moment about the same point. I think they asked this question in 2003. I think why 2003? That why 2003 or 2004. Within that, in 2003, 2004, 2000, one of the years, they asked this question. That students should state the conditions of equilibrium under the action of parallel coplanar forces. And that is what you expect to do. That means for a body to be at equilibrium, for a rigid body, the forces acting in one direction must be equal to the forces acting in the opposite direction. What I mean here is that if I have this and I have forces acting in this direction, I have F1, F2, sorry. I have F1, F2, then at the downward here, I have F3 and F4. Can you see my board? Daddy, can you see my board? Can you see what I've written?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now, the forces on my upward direction must be equal to the forces on my downward direction. Then the body will stay. The body will be stationary. But once, it's just like, I gave you an instance. Now, if this is my posture, if I'm walking like this, I'm not at equilibrium because this shoulder is higher than this. You know, some people walk like that, isn't it? But for my body to be at equilibrium, my shoulder must be squared, like models. In modeling, it's applied in modeling. Now, in modeling, models are expected to have square shoulders to walk. Okay, if you look at them, they walk like Robert. Can you see that they walk like robots? Why? Because they must have square shoulders. Their shoulders must be at equilibrium. Thank you. Next, we have conditions for equilibrium of rigid bodies under the action of non-parallel coplanar forces. Non-parallel coplanar forces are forces that take the sides of a triangle. Non-parallel coplanar forces are forces that take the shape of a triangle, like a bucket. A bucket is a non-parallel coplanar force. Look at the size of this, my sketch, the sketch of my bucket. Look at this. If this is my bucket, and this happens to be the handle, and two students are to carry a bucket of water. Let me redraw this for you. Now look at this. If this is my bucket,
Oh, Jesus.
now if this is my bucket, the size of my bucket, look at this carefully. Now in the hostel, now if there are some students that cannot carry a bucket of water, they will ask their friends to help them. Now if one student holds the bucket by this side, another student holds it by the other side, there are three forces that act on it. Number one, I have tension 1, T1, and I have tension 2, T2. Then I have the weight acting downwards. This is a non-parallel coplanar force because this bucket has the orientation of a triangle. How? It has the orientation of Y like this. This is what it has. T1, T2, T2, and the weight. The weight is acting downward like this. So what is the orientation of a triangle? Now look at this now. The orientation of triangle is equivalent to, look at this triangle, this arrow that is drawn downward. I will draw it downward. Look at this line that went the other way. I will draw it that way. Then look at this one that went this way. I will draw it this way. This is the three non-parallel coplanar forces because it takes the orientation of a triangle. You see it now. So now look at it. The forces must be concurrent. Concurrent, that means they must be following each other. Look at it. T1, T2, W. This is W. This one that went this way is T2. This one that went this way is T1. You see, they are following each other, so they are concurrent. They must be following each other. Then number 2, the resultant forces must be equal to 0. The resultant forces must be equal to what? 0. What they are trying to tell you in essence, if you add 1, 2, 3, everything will be equal to 0. Because they are at equilibrium. Then the next, the forces can be represented in magnitude and direction by the three sides of a triangle taken in order. Taken in order. And that third point is talking about Lami's theorem, the triangle of forces. The triangle of the last one is talking about what? The triangle of forces or Lami's theorem. And Lami's theorem states that if three forces are acting at equilibrium, then they can be represented in magnitude and direction by the three sides of a triangle taken in order. It says that if three forces, force 1, force 2, and force 3, are acting at equilibrium, this is force 1, F1. This is force 2, F2. This is force 3, F3. If three forces are acting at equilibrium, then they can be represented in magnitude and direction. Magnitude means the size of the force. Direction means angles of the forces. Now, if three forces are acting at equilibrium, then they can be represented in magnitude and direction by the three sides of a triangle taken in order, like this. This is direction 1, direction 2, direction 3. And you did that in mathematics. In order to solve point 3, you use sine rule. Use what? Sine rule. Where you were taught something like this, they say sine capital letter A over small letter A is equal to sine capital letter B over small letter B is equal to sine capital letter C over small letter C. Where A, capital letter A, capital letter B, capital letter C represents the angles, the directions. Small letter A, small letter B, small letter C represents the forces or the magnitude of the force. That is the third point. So we're solving questions using point 3. Point 3 is talking about what? The triangle of forces or Lami's theorem. Okay. So now we have center of gravity. Center of gravity is defined as the point through which the resultant weight of an object appear to be concentrated. It is determined by balancing methods. Every object has its own center of gravity. Like, look at this. Now, if I want to find the center of gravity of a square, is the point of diagonal. The point where the diagonal lines meet is the center of gravity. That's the center. Once you draw diagonals, the point where the point of intersection of the diagonal line is the center of gravity, including a rectangle. A rectangle too is the point of intersection of the diagonal lines. Will give us the center of gravity. Okay? Then a meter rule. The center of gravity is at the 50 centimeter mark. Okay? So now, any questions so far? Because we still have positions of equilibrium. We'll do this in our next class because of our time. So if you have any question to ask me, please ask. Before I give you, because we've done this in SS1. Before I give you my assignment. Oh, yeah, any questions so far? Derek, question? Isaac, question?
No, sir.
Okay.
No, sir. No, sir.
Okay. Achem, Esther. Any question? Esther Peters.
Thank God, no comment.
Aliu.
No questions, sir.
P. Samuel. Buzu. Questions?
No, sir.
Okay,
No
now
questions,
these are
sir.
my questions. Define the term equilibrium of forces. These are my evaluations. List the types of equilibrium. I've not explained that, but we have stable equilibrium, unstable equilibrium, and neutral equilibrium. Then state the principle of moment. Then list examples of couple or the applications of a couple. So this is your assignment. So you're going to use turnout. Use turnout.
Yo.
Use turnout. So I'll give you my reference. My reference. Use turnout. Use turnout. donut Q and A. Use donut Q and A. Are you with me? Hello? Achem. Now look at my questions. Now, you are going to answer this question for me. Write your name. Get a foolscap sheet. Write your name,
Bluetooth,
your class, then topic. The answer WAEC to 1997, question 9. It's an objective question. Then WAEC 2007, question 11, essay page 161. Then go to WAEC 2011, question 10, objective, page 192. WAEC 2014, essay, question 11, objective question 11, page 216. WAEC 2016, question 10, objective, page 237. WAEC 2017, question 9, essay, page 249. Use donut. Don't use any other one. Use donut. Don't use unique. Is that taking? Ali, I hope you have donut with you.
Don't leave me.
Yes, sir.
Do you have
Don't
donut?
use unique.
Yes, sir.
Okay, so do that for me, please.
Don't leave me.
Now, in the absence of any question, we'll call it a day today. Okay?
Don't leave
Then
me.
our next class, I'll continue with center of gravity, position and locations, types of equilibrium. Then we'll solve some numerical problems. Okay? But please do this.
Right?
Write it on a foolscap sheet,
Right.
snap it, and send it to my
Right.
contact.
Christiana Nini Buzun.
Are you with me?
Gemma Lela Buzun.
Are you with me? Thank you very much. And
Jessica,
God bless you
Natasha
all.
Buzun.
Let's pray in
And
Jesus'
Joel-
name. Father, we
Joel
thank you
Buzun.
for today.
All of
Thank
you.
you for this
Buzun.
class. We ask for your grace to recall all we've studied today. In Jesus' mighty name. Amen.
Mozuno.
Buzu da cast.
Bad guy.